Here is our rates and equilibrium practice test number 2. Question 1. The diagram to the left, or to the right as this actually is, shows an energy profile diagram for the reaction 2A plus B forms C. So here's our energy profile diagram. Let's look at the questions. Determine the value for the activation energy in the reaction above. So I'm guessing we're going with a forwards reaction here. So activation energy is from where our reactants are to here, and that is the difference between 200 kilojoules and 250. So it's going to be positive 50 kilojoules. All right, and that's probably 50 kilojoules per mole of reaction. All right, but the idea is it's going to be from here to here, and it's going to be 50 kilojoules. Write a thermochemical equation for the reverse reaction. So we want to go backwards from products to reactants. So looking at this, that means we're starting out with C. We're going to still be in an equilibrium process because it's an equilibrium reaction. That's going to form B, which is a gas, and 2A, which is also a gas. Now, it's a thermochemical equation, so therefore we need the delta H as well. What is the delta H for our reverse reaction? Our delta H here is the difference between our reactants and our products. So this here is 100 kilojoules per mole. Now in the forwards reaction, that's exothermic, makes it negative, but our reverse reaction is endothermic. So we're going to have to put in 100 kilojoules. It's going to be positive 100 kilojoules per mole for the reverse reaction. So understanding that we're looking for the reverse reaction there. With reference to Le Chatelier's principle, discuss how the yield of molecule C will be affected by, all right, so we want to find out how much C is being produced if we add more B molecule. So let's go through our process here. Now what happens if I add B? Add B, that's adding a reactant. Addition of B increases, so we're going, all of a sudden there's an instantaneous increase in the concentration of B. Le Chatelier's principle states that the reaction will partially oppose this and favour, well, if we want to partially oppose the addition of B, we want to use up B, so it's going to favour the forwards reaction. Favour the forwards reaction. And what does this do to molecule C? If favour the forwards reaction, it means that the amount of C will increase. Therefore, the yield of C will increase. The idea here is, if we need to talk about Le Chatelier's principle, we need to be talking about how the reaction is going to partially oppose the change. So what was the change? What is the partial opposition? And why does this? And therefore, we have molecule C. Partially oppose this and favour the forwards reaction. I'm going to say here maybe as well, to reduce concentration of B. So for partially oppose that, favour the forwards reaction to reduce concentration of B. Now let's look at the next one. Increasing the temperature of the reaction vessel. So if I increase the temperature, okay, Le Chatelier's principle states it will oppose this by favouring, all right, so how do we favour an increase in temperature? We need to decrease the temperature, so therefore we need to favour the endothermic reaction. Thus, the reaction moves which way? So forwards is exothermic, so it has to go in the reverse reaction. In the backwards, the reaction moves backwards, and the yield of C, well, if I favour the backwards reaction, I'm going to be using up C, so the yield of C will decrease. With an increase in temperature, we want to favour the endothermic reaction. The reaction moves backwards because that is the endothermic reaction, which decreases C. So therefore, these are basically questions out of 3. So you want to state 1, what is going to try and happen? It's going to partially oppose this. which direction is it going to favour, and what impact does that have on C? 1, 2, and 3 for these marks. Last question in question 1 is discuss how decreasing the size of the reaction vessel will affect the rate of the Ford's reaction. Alrighty, so what happens to decreasing the size of the reaction vessel? So if I decrease the size of the reaction vessel, all concentrations will increase. So we need to look at this in terms of what happens initially, what does Le Chatelier's principle say, and then what is the actual overall effect on the rate of the Ford's reaction. So if I increase all concentrations, so initially the all concentrations will increase, thus the Ford's reaction rate will increase due to the higher frequency of collisions. Again, whenever we're talking about rate of reaction, I like to bring in this term of frequency of collisions. And I should put in there successful collisions, full collisions. Okay, so initially this is what happens. Le Chatelier's principle states the concentration increase will be partially opposed by favouring the side with less particles, which is we've got 3 particles on this side, only 1 particle on that side. So that is the Ford's reaction. So that's what Le Chatelier's principle says. Now, what will happen to the Ford's reaction? So then this means, therefore, the concentration of our reactants will start to drop, and therefore the rate of the Ford's reaction will also start to decrease. However, it will remain higher than it was before the change. Now let's just read through that again and make sure you understand this. So, discuss how decreasing the size of the reaction vessel will affect the rate of the Ford's reaction. I need to then discuss what's impacting the rate of our reaction. Initially, the size will decrease, therefore all the concentrations increase. That creates the rate of reaction. That means the rates of the Ford's reaction will increase because we're pushing everything closer together. Le Chatelier's principle, which is the second part of my discussion here, will say that the reaction will oppose this increase in concentration by favouring the sides with less particles. So therefore that means the Ford's reaction is favoured. Now this is a partial opposition, so therefore our reactants start to be used up, but we still have a higher concentration than we did initially. So therefore our rate of reaction to the Ford's reaction will start to decrease. However, it remains higher than it was before our change. So if I was to look at that in terms of a graph, which is always a good idea, graphs are great for this. This is our Ford's reaction here. It's at equilibrium, and then what happens, it sharply increases due to the size condensing. And then the Ford's reaction is favoured, so my reactants start to get used up, so therefore the Ford's reaction decreases until we reach equilibrium again. And that's my little graph there, showing what I've just discussed in words here. Hopefully that makes sense. I'll probably over-analyze this question. However, better safe than sorry. Always looking at what initially happens, what does Le Chatelier's principle say, and what happens on the way back to equilibrium. That's what this question's all about.